Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Boundary Values Behavior 2. And as always, please be an active learner as you watch this video. By way of introduction, there are many more applications of wave phenomena in physics than just sound waves. Some things are the same and some things are different. But enough is common, and so much can be learned from the slight differences that we will talk a bit about electromechanical waves here before returning to sound waves within this lecture. Introduction to electromagnetic waves. When electrical and magnetic fields vary with time, they're not independent, and in fact, they cause waves. This two-way interaction between the two fields is summarized elegantly in a set of 4 equations now called Maxwell's equations. We won't study these equations directly because their mathematical complexity is significant, but we will explore the primary prediction of these equations, that the phenomenon called electromagnetic waves. When either an electric or magnetic field is changing with time, a field of the other kind is induced in the adjacent regions of space. In this way, time-varying electric and magnetic fields can propagate through space, propagating through space as a wave. Such propagating disturbance is called an electromagnetic wave. There is talk here in this paragraph about some of the experiments that Heinrich Hertz did, and that's who we name the unit of frequency after is Hertz. But notice that these are similar in at least structure. We end up having a wavelength. We also have the relationship V equals lambda F. Those are true for any wave phenomenon. And the SI unit of frequency, 1 cycle per second, is named Hertz in honor of the great German scientist. And I always capitalize this. They did not right here, but I always capitalize it because it is a proper name. So what are the characteristics of such a wave? Well, this wave is transverse. That is different than the longitudinal sound waves. But remember that even the longitudinal sound waves, if you're measuring some related thing caused by the sound, such as pressure, that wave can be transverse. There's a definite ratio between the magnitudes of the electric field and the magnetic field. Notice these are vectors, and that ratio is a constant c. And in fact, that c is the speed of light in a vacuum. So the wave travels in a vacuum. It doesn't need a medium like sound, with a definite and unchanging speed c. Unlike mechanical waves, which need the oscillating particles of a medium such as water or air to be transmitted, you see sound does require a medium in space. No one can hear you scream. Electromagnetic waves require no medium, and so it's the fields that are waving, not the medium. And there's a calculation in your book. We will just take this as a given rather than going to the underlying aspects of this calculation. But the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. Let's do some calculations with this stuff. And we want to get a feel for how fast light really does move. So let's begin by calculating the distance the light travels in 1 second. But we want to change the units. This is a dimensional analysis problem. And we want to express the answer in units of circumference of the Earth. And we make note that the equatorial circumference of the Earth is 4.01 times 10 to the 7th meters. And let's solve this problem. Okay, so distance is equal to velocity times time, and we're taking that to be c times t. And we're talking about speed of light in a vacuum. So c is 3.00 times 10 to the 8th meters per second times 1 second, and that is 3.00 times 10 to the 8th meters is how fast it travels in 1 second. But now we want to use dimensional analysis to change this distance into circumference of the Earth. So we take 3.00 times 10 to the 8th times 1 circumference of the Earth per 4.01 times 10 to the 7th meters. The meters cancel, and we find that is 7.48 circumferences. That means that light is so fast that it would travel between 7 and 8 times around the Earth in 1 second. In part B, we calculate how much time is required for light to travel 1 foot. Well, we wouldn't expect this to be very long, but we're going to say here we had distance equals rate times time. Here we're going to solve that for time. Time is distance over rate. And 1 foot is changed to meters here, so that is 0.3048 meters divided by the speed of light. And the if you do the units, you do get seconds, and it's 1.02 times 10 to the minus 9 seconds. And here's a sample problem that you wanted to do if you might want to do if you want to practice this consideration. That's at the bottom. Electromagnetic waves cover an extremely broad spectrum of wavelengths and frequencies, and you can see this in this table, and together these are called the electromagnetic spectrum. So look, this wavelength in meters goes from 10 meters for radio and TV waves down to 10 to the minus 13, and actually further than that in wavelengths in meters. If we look at those wavelengths in terms of frequencies measured in hertz, you see that those range from 10 to the 8th hertz all the way down to 10 to the 22nd hertz. But like sound, where only a small portion of the sonic spectrum is where you can hear it, only a small fraction of this is visible light. But here you do see different colors, ranging from red on this end to blue on this end. In fact, this is why the sky appears blue, is because of equations stemming from this. There are many other applications, though. These are like the communications applications of television signals and radio signals, but then we have microwave transmission for communications and otherwise, and these are the same microwaves that you use to cook with. Infrared, you use these for remotes and other things. Ultraviolet, the sun gives you ultraviolet, and in fact when you use sunscreen, you're protecting yourself from these rays that you can't see. X-rays are known, and gamma rays are powerful things up here. Now, that's the spectrum. And all of these are the same principle. They differ in frequency and wavelength, but the relationship, and this general relationship was velocity is equal to lambda times f, but in this case, when we're talking about the speed of light in a vacuum, this is c. The speed of light is lambda times f. And one example of this is that the color, and I talked previously about why the sky is blue. This little piece could be why are plants green. The green color of plants is directly related to photosynthesis. Plants are green because green is the color of light that plants don't use during photosynthesis. As you can see from this graph, I'm not really showing you the graph, the plant molecules absorb all these other colors. This contributes to building sugar molecules, but they do this for everything but the green. The green is not absorbed and is reflected and transmitted. So the plants appear green. The frequency or wavelength then is lambda is equal to c over f from that. And so if we wanted to think about for visible light, where a typical frequency is 5 times 10 to the 14th hertz, the corresponding wavelength is, so we take the quotient of the two, there's the speed of light, there is the frequency, and we get 6 times 10 to the minus 7 meters, and that can be changed to nanometers, and that's 600 nanometers. And that's about the size of some bacteria, and 1/100th the size of a human hair. That's talking about the diameter of the human hair. And so that gives you an indication of these wavelengths are, in fact, sometimes very small. But they can also be significant because if you're talking about the frequency of 10 to the 8 hertz, that's typically what an FM radio station will be transmitting at. The wavelength is, there's the speed of light, there's the frequency that we're talking about, that is going to be 3 meters. Like an extreme range of many orders of magnitude in wavelengths. Let's look at another example. When you punch a button on your remote control, it emits a series of electromagnetic radiation. Your TV then decodes it and changes channel and so on and so forth. So suppose a remote control for a TV emits a radiation with a frequency of 1.0 times 10 to the 14th hertz. This is in the infrared range. Calculate the wavelength of the radiation it emits. And also identify the corresponding region of the electromagnetic spectrum by referring to this. And can you see this radiation? Okay, well, again, as frequently is the case, lambda is equal to C over F. And again, we're talking about this happening in a vacuum, and it turns out that light travels differently in different mediums. We'll talk a little bit about that. We're just using the speed of the vacuum here as an approximation. So we take this divided by the frequency, and we get that this is 3 times 10 to the minus 6 meters, and if we change that to nanometers, this is 3,000 nanometers. This is in the infrared spectrum, and you cannot see it. And here's another problem if you wanted to practice this kind of calculation. There's also a phenomenon called radiation pressure. When an electromagnetic wave is completely absorbed by the surface perpendicular to the direction of the propagation of the wave, what we end up with is something called radiation pressure, because it's average force per unit area, or simply pressure, and that is equal to the intensity divided by the velocity. And so if we look down here, then the radiation pressure is intensity divided by velocity. Here is the pressure unit, and we're dividing that by this speed unit, and we end up with, in fact, I should have set this up a little better here. So for example, the value of I for direct sunlight before it passes through the Earth's atmosphere, so you are in a vacuum, is about 1.4 kilowatts per square meter. And so we have 1.4 kilowatts times, and we're changing this into watts, so that's times 10 to the 3, that makes it the kilowatt per square meter. But then when we divide that by the speed of sound in a vacuum, we get that this is the number of pascals. It also is a useful dimensional analysis exercise for you to see if you can work with these units to come up with pascals. Now, I should have said more. So this is equal to I over C whenever the surface absorbs the light. If it is reflected, what happens is the pressure is 2 I over C. This 2 is similar to how come we get a 2 in the Doppler equation that we used in ultrasound. So the average radiation pressure on a totally reflecting surface in this same scheme is twice that. So this is 2I over C, or this would be 4.9 times 10 to the minus 6 Pascal. Now these are very small pressures, they're times 10 to the minus 6, but they can be measured with sensitive instruments. And in fact, we're going to use this to solve a problem. So in this example, we investigate, is it possible to use radiation pressure to propel a spacecraft? So, suppose you had a spacecraft with a mass of this 2.50 times 10 to the fourth kilograms, but you have solar cells and you're traveling in space, you're traveling in a vacuum, made perfectly reflective. So this, and this is a specialized film. And this has an area of 2.59 times 10 to the 6 square meters. And that's a square mile. Now this is a very big solar cell. But if the spacecraft is launched into Earth orbit and deploys its sail at right angles to the sunlight, that means it gets all of this, what does acceleration do to the sunlight? And the Earth's distance from the sun, the pressure exerted by sunlight on an absorbing medium is 4.7 times 10 to the minus 6 pascals. We did this calculation before. Okay, so here's the area that you have, and this is the pressure. And we know that force is equal to pressure times area, because pressure is force divided by area. We know that this is a factor of 2, as we discussed in the previous example. So we divide this pressure by, or we multiply this pressure times the area, and we get that's 24.3 newtons. And so now we find the magnitude of A by solving F, the net force, divided by the mass gives you the acceleration. So the force was this, we got that from here, divided by the mass, and that gives us an acceleration of this. Now you might say, well, that's a puny acceleration, but we can reflect on that, and this is 9.72 times 10 to the minus 4th meters per square second. Now for this spacecraft, a square mile of sail provides an acceleration of only that. And that's small compared with accelerations that you could get with chemical rockets and things like that. But the rockets will burn out and the fuel will burn out, but sunlight keeps pushing. So, and this will get faster and faster and faster. Even on the first day, this spacecraft would travel more than 3,000 kilometers in the direction that it's pointing. On day 12, its radial speed would exceed 1 kilometer per second. Very fast. Here's a practice problem if you wanted to try more of these kind of calculations. The pressure of the sun's radiation is partially responsible for pushing the tail of a comet away from the sun. Here's where a comet coming in, and this solar pressure pushes the tail of the comet from where it would sit here to over here. So there is some empirical and experimental verification that that is indeed a phenomenon that we do observe. Let's test our understanding. If you double the frequency of an electromagnetic wave traveling in a vacuum, we're traveling in a vacuum here, which the following characteristics will not change. And you have a multiple choice. And since the speed of an electromagnetic wave in a vacuum is a universal constant, that's the product of these, and it does not change. Therefore, the wavelength will decrease by a factor of 2. The period of the oscillation will also decrease by a factor of 2. However, the average intensity of the wave is independent of the frequency and wavelength, so the correct answer is C. All of these discussions stem from C equal lambda times F. A laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. The term laser, in fact, is an acronym for light amplification by stimulated emission of radiation. The first laser was built in 1960, and now it's a big deal in surgeries and telecommunications and other applications. Now, a significant characteristic of the laser weight is that it is much more nearly monochromatic. That means it is a single color. That means it is a single wavelength. Some telecommunication carriers will, in fact, launch into fiber optic cables a couple of different wavelengths, and thereby significantly increasing the capacity of the communications channel. That will be it for now. So now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.